So a follow-up on the cross product is that we can use the cross product to help us find the volume of a parallelepiped. And that's a big word that just means basically if we took a parallelogram and we made it three-dimensional, so kind of like a parallelogram prism. Okay, so let's draw what that looks like a little bit first. Okay, so let's say I have, again, a vector B and a vector A. Okay, and I can draw the base of that parallelogram that way. And that was what we talked about last time. Remember that the cross product will give us the area of that base. But if we want this to be in 3 dimensions, we need a third vector. We'll call it C. Okay, and then if I sketch this out a little bit, you can see that we are making a prism with faces that are parallelograms. That's actually not bad. Okay, so I want to find the volume of this figure. Well, we know that volume is usually area of the base times the height. And that's not dot product, that's just a multiplication symbol. Now, because this is in space, okay, doing the cross product or doing a dot product or something like that could give us something negative. Okay, so we want to make sure we take the absolute value because we don't, in reality, negative volume doesn't make sense. Okay, well, I just said this, but we know how to find the area of this base. Let me shade that in a little bit. Okay, I could find the area of this base using the cross product. So I could say that the volume is equal to, just say V for volume. Volume is equal to, remember, the magnitude of A cross B. Okay, and then times some height. Okay, remember we have to take the magnitude because just crossing A and B will give us a vector, and we want the magnitude of that vector to give us this area. Okay, well, how to find the height? Well, unluckily, since this is a parallelogram faces, C is not at a right angle, so we couldn't just take like length C and make that our height. We basically want to find out how much of C goes in the direction perpendicular to A and B. How much of a vector goes in the direction of another vector? That sounds just like the component, okay, we've talked about with the dot product. So what would be nice is if we could replace height with the component of C onto this vector that is perpendicular, but we don't know what this vector is. Well, another great corollary of the cross product is that A cross B, that vector we're taking the magnitude of here, is actually perpendicular to both A and B. It's perpendicular to that parallelogram. So this vector right here is A cross B. A cross B is, let's summarize, perpendicular to A, perpendicular to B, and it has magnitude that is equal to the area of this parallelogram, okay? We're not really worried about the area except for this part, the area of the parallelogram except for in this part. Right now, we're using this as a vector that we could project C onto. Remember, we're trying to find the height. We're trying to find how much of C is going in a direction perpendicular to this parallelogram, okay? Well, that would be great if I knew what this angle would be. And we could try to find it if we knew the angle between C and the plane, but I know that we have a different definition for the component. If I'll remind you, the component of some vector, let's call it Q, to use a variable I haven't used here, onto P, okay? The component of Q onto P is the dot product, P dot Q, divided by length P. Okay? All right, So using this definition and using the fact that I want to project C onto A cross B, that will give me how much of C is going in the perpendicular direction. So I can replace height with C dotted with a vector A cross B, which I have not named, I'm just leaving it as A cross B, divided by length A cross B. Okay, let me say that one more time. This formula right here is the component of C, this vector C, onto A cross B. And that will give us the height. How much of C is going in the perpendicular direction to A and B. You can even think about it like this. Okay, if you did a little dotted line down. We were trying to look for that Y, almost like, I guess in 3 dimensions it would be the Z component. Okay? All right, and then over here, excuse me, let's make sure I'm being consistent about my magnitude notation. We had still the magnitude of A cross B, which is the length, magnitude of A cross B, which can also serve as the area of this base. Well, if we take a look, we can simplify our formula by eliminating those two. And so what's left is just C, the vector, dotted with A cross B, which is a lot simpler. Okay, well, what does that look like? Okay, well, let's try to figure out what A cross B looks like first. And this was from our last video, but I'm gonna give myself some more room. Okay, so that volume formula, you could leave it here if you would like. But in general, I just wanna show you a little bit more expanded form. So I want to dot the vector C, okay, with I, A2, A3, B2, B3, minus J hat, A1, A3, B1, B3, plus K hat, A1, A2, B1, B2. Okay. Well, remember that when we dot vectors, and this is a vector, okay, oops. Okay, what I do is I multiply each corresponding component. Okay, so let's say that, let's give C some components, C1, C2, C3. Okay, when I dot these two vectors together, really what I'm gonna get is a scalar. So I will get C1, and then the determinant of this matrix, minus C2, plus, oh, not K hat, excuse me, C3. Okay, and that is a scalar. Notice I didn't put any vector brackets on it because that's a scalar value. Well, if you think back to our definition of the determinant, this is actually this expanded version of the determinant of C1, C2, C3, A1, A2, A3, B1, B2, B3. A little crooked. Okay, so this is really nice. You can think of the volume of a parallelepiped in 2 different ways. You can think about it as the determinant of the 3 vectors, A, B, and C, or you can think about it as the dot product of the vector C and the vector A cross B. Sometimes it's easier to think about it this way and take it one step at a time, but sometimes if you feel really confident with determinants, you might just want to put them all in there together. Okay? That's the volume of a parallelepiped.